Hi everyone, my name is Anna and I'm back again with another video about heat and mass transfer, and today I'm going to be talking about two different things. So it's kind of going to piggyback off of the third video that I made, part C, that was talking about resistances and relating heat transfer to change in voltage through a circuit. So today we're going to be looking at how we can write our Fourier's law in terms of resistances in series versus resistances in parallel. And then I'm also going to do a specific example related to looking at them in parallel. So first we're going to talk about an example in series. So I'm going to rewrite the example that we looked at in that other video where we could see the resistances in series. So that was the example with our coffee cup. So we had our coffee that was enclosed in a glass cup that was enclosed in insulation that was then exposed to ambient air. So this is just our example again. I'm just drawing it pretty easily, very simple. So we're just imagining we have coffee, liquid coffee, touching a glass surface, and that glass surface is touching an insulation surface, and the insulation is touching air. So I'm going to go ahead and write the different temperatures that we're going to see in these different units. So the coffee is, I'm going to write as our T initial, so just T in. Actually, I'm just going to denote it as Ti for initial. And then our air is our final temperature that we're trying to find, so that's Tf. And then at each of our interfaces, we're going to have a different temperature there. So I'm going to do the interface between the glass and the coffee as T1, between the glass and insulation as T2, and between the insulation and air as T3. So this is just what I've written so far. So we had, sorry, it's really hard to see that I, the dot over the I, but under coffee it says Ti, and then between coffee and glass, T1, glass and insulation T2, insulation and air T3, and then the air is Tf, or final temperature. So these are the different temperature interfaces that we're going to see. So when we're analyzing our resistances, and trying to see the changes in these temperatures, we have some sort of variable now written here that will make it easier for us to look at. And then for each of these, but the length between where the glass touches the coffee and the insulation is going to be its own length. So I'm going to denote that as Lg, or length of the glass. And then same thing with the insulation, that's going to have some certain length between where it touches the glass and where it touches the air. So I'm going to denote that as Lins for insulation. So we just have that as well. And if you remember from the other video, we said that the heat flow, so the heat flow is going to be going from the coffee to the air, because we go from areas of higher temperature to areas of lower temperature. So that heat flow is going to go from coffee to air, but we're going to denote our positive x direction as being from left to right, which is what you would traditionally think of in a system. So I just wrote that as well on the bottom. And then if you remember, our heat flow is going to be the same at each of these interfaces. So our Q, I'm just going to denote it as Q because that's easier than Q total, because we aren't necessarily adding all of these heat flows up. It's just a constant heat flow that's going to occur from the coffee to the air, or throughout our entire system. So Q is going to equal the heat flow that occurs at the coffee, which is convection. So I'm going to write that as Q. This happens through convection at the coffee, so CONV, comma, C, which is going to be equivalent to the heat flow or heat flux due to conduction between the coffee and the glass. So I'm going to say Q conduction, COND, G for glass, and then Q for conduction between insulation and the glass, I and S, and then the Q convection that happens at the air. So just A for air. So this is what I have written here. So we recall that the heat flow throughout the system is constant, so it's going to be equivalent to whatever heat flow we have at the coffee, whatever heat flow happens between coffee and glass, between glass and insulation, and between insulation and air. So we can recall that Q convection is equal to HA dt, and Q conduction is equivalent to negative Ka dt over dx. So these are just equations that we already know, just writing them back down again. And just to do a little review, we have our delta V equals IR, and we want to get our Fourier's law written in terms of, in the same format, I guess I should say, as delta V equals IR, and I is our current in a resistor, which is very similar to our heat flow because current is going to be flowing through a resistor and heat flow is going to be flowing through our system. So our heat flow is going to be essentially symmetric, I guess, or comparable to the current in a system. So we want these to be in the same position. And then our delta V, which is voltage gradient, is very similar to our delta T, which is our temperature gradient. So we want these to be in the same position as well when we write these equations. So I've just written that the I, which is current, is essentially similar or comparable to the heat flow, and the voltage gradient is essentially similar or comparable to our temperature gradient. So we can rewrite our convection and conduction Fourier's equations to match the same format as the delta V equals IR equation. So Q convection equals HA dt. We'll move our dt over so that that equals, I'm going to change the d in dt to a delta symbol as well, just to make it even easier to see the similarities. So delta t equals, and then we'll have Q through convection times 1 over HA. And then that's going to be delta V equals IR. So I've just written here that our Q through convection is HA dt. We moved our delta T to one side, and then we have our heat flow through convection times 1 over HA. So in this case, 1 over HA is going to be our resistance through whatever material, whatever interface we're looking at via convection. Then for conduction, we'll draw this arrow down here. Q conduction equals negative Ka dt over dx. So we'll go ahead and move that delta T over again. So we get the delta T equals Q conduction times, and then this time it's going to be our delta X in the numerator over Ka here. And we do have a negative there as well. So in this case, delta T, same spot as delta V, and Q through conduction is same spot as our current. And then our resistance is going to be equivalent to the change in position, delta X, over negative Ka, which is thermal conductivity and surface area, cross-sectional area, I guess I should say, not surface area. So for convection, our resistance is going to be equal to that term. So if we want to rewrite our entire system in terms of these resistances that we've found, it'll be quite easy now. So I'm going to go ahead and write it for each of these examples. So Q, convection of coffee, that's going to equal, so we recall that Q convection equals HA dt. So if we write this in terms of delta T and R instead of all of the other variables, we would get delta T over R of the coffee. So since we just solved to show what all encompasses the resistance for a convection example versus a conduction example, we're just going to denote it as the resistance in general now, because we solved for those resistances. So the resistance for convection is 1 over HA. And since we're trying to write this in terms of I equals, that would be I equals delta V over R. So that direct translation is going to be Q equals delta T over R. So we have our Q through convection equals change in temperature over the resistance of the coffee. And just going to write on the side that this is the same thing as 1 over HA. So if we plugged the 1 over HA back in for the RC, we would get Q convection of coffee equals delta T times HA, which is the same as our original equation for convection. So that's going to be correct. And then the Q through conduction of our glass is going to be delta T over RG. So this is the same circumstance as the one before. RG is going to be delta X over negative Ka. So if you plug that back in, you would get delta T times negative Ka over delta X, which is once again in the same format as our original Fourier's law for conduction. So I'm going to write these for the other two. Q conduction at insulation is going to be delta T over the resistance at the insulation. And then Q convection at air is delta T over RA. So those are just our last two down there. That's just our simplified version with the other two variables being encompassed in our resistance term. So then if we want to find our final resistance, we can do the net resistance. Since this is in series, this example is in series, and that means that in order to get from the coffee to the air, you have to pass through the coffee, the glass, the insulation, the air, one at a time. So these can all be added together as if they're in series, the same way resistors that are in series in a circuit can be added together. Also, the writing on the back here is from another video, not this one, if you're wondering. So then we can just add up the resistance at the coffee plus the resistance of the glass plus the resistance of the insulation plus resistance of the air. And that's going to equal our R net here. So now I'm gonna actually expand this out so we can really see exactly what we're looking at here. So our R net is gonna equal, so the resistance of the coffee, as I mentioned before, is 1 over HA. So the H is gonna be our, our conductivity coefficient. So I'm gonna say HC because the H at the coffee is going to be different versus the H that is used at the air. Plus the resistance of the glass will be our delta X, which if you remember before, we actually dedicated what that length was. So instead of putting delta X, we can put length of the glass, because that's our delta X here, is we're looking at how wide that glass piece is. And then that's going to be divided by negative K of the glass. And this is the same instance as the conductivity coefficient, the thermal conductivity, the convection coefficient. The thermal conductivity is also going to be variant depending on whether we're looking at the glass or the insulation. So we'll denote that as the thermal conductivity of the glass times the area plus the resistance of our insulation. That is going to be the length of our insulation divided by negative K of our insulation times area plus the resistance of the convection of the air, is going to be the 1 of H, the H of the air times area once again. So this is our net resistance expanded out. So I just wrote them for each of the corresponding terms. So the first one's for coffee, the second one's for the glass, the third is for insulation, and the last is for the air. So that's just kind of showing you what exactly these resistances are made up of, like what components they are. Now, we can go back to our delta V equals IR equation, and we can see, we can rewrite this as our delta T equals QR. I'm just representing all of these resistances again with the letter R to make that easier. So if we want to just skip all the interfaces, we don't want to look at every single interface and evaluate all of that, we can actually use our net resistance to go straight from the coffee or the temperature initially to find whatever temperature it's at in the air, so the final temperature. So we can rewrite the delta T equals QR equation, by writing the temperature final, which is the temperature at the air minus temperature initial, equals, and then we have our heat flow, which if you remember, once again, is going to be a constant throughout our system, so that can equal the heat flow that we find at any of those interfaces or at the coffee times our net resistance. So this is what I have here. Our delta T, temperature final minus temperature initial, is going to equal our heat flow times our net resistance. So that's going to encompass our entire system in order to jump from one end to the other without having to look at every single little resistance or interface in this case. All right, so that's kind of our main idea here. if we're looking at the resistances in series, so we can just add them all together as if we're looking at a circuit in series, which makes that nice and easy. But now we're going to look at a parallel example. So if we have our system with units that are in parallel with each other rather than series. So I'm going to write, I went ahead and changed pages. This is our parallel example. I'm going to do a pretty simple example first, just two materials that are in parallel with each other, rather than jumping to our final example, which is going to have multiple different components that are in parallel and series with each other. So the parallel example, I'm just going to write here that we're going to have brick. So this is going to be a wall, and we're going to have brick on one side and then concrete on the other. Actually, I did not say that well, but the brick is going to be on top of the concrete this way. They're going to be stacked on top of each other rather than perfectly side by side. And then on one side, we'll just have some sort of heat source, something that's providing heat. I'm just going to say heat, for example. And then on the other side, that's going to be exposed to air, once again. So we just have our heat and our air. And we're still going to have our heat flow from areas of hot to cold. So that's going to go from the heat towards the air. And our goal here is to, once again, write this equation to find whatever the initial heat is, to see what the final temperature, the air temperature is. So we're solving for the heat flow here again by doing delta T equals heat flow times our total resistance. So now we're going to analyze what our total resistance is if these are stacked on top of each other, or aka they're in parallel rather than just in series where they're side by side to each other. So we have our example written out now, and we can start to look at these resistances. So when we're looking at resistances, the total resistance in parallel, you might recall that this is going to equal 1 over whatever resistance plus whatever is the next resistance. So this is how our total resistance is going to look if we're adding things up in parallel. And from before, just a reminder, the resistances in series is just the R1 plus R2 plus blah, blah, blah. So there's definitely a difference in how you get to your final resistance if it's in parallel versus series. And right now, our brick and our concrete are in parallel with each other. They are on top of each other, which means that the heat that's flowing from our heat side can go through both the concrete by itself or the brick by itself. And it's going to have to go through both of them in order to get through to the air. So we're going to have to add these in parallel with each other. So we can write our Q conduction at the brick as equaling negative Ka dt over dx. And if we reshape this to be in the delta T equals Q conduction of the brick is going to be our delta X over negative Ka. So this is just rewriting our heat flow through conduction at our brick in the same format as the delta T equals Q, and then our resistance, which is dx over negative Ka. So we have here, this is the same format as delta V equals I R once again, and then our Q conduction of our concrete is once again negative Ka dt over dx. And so our dx's will actually be the same with these two because they're stacked on top of each other. They're going to have the same width. But our thermal conductivity, which is our K, is still going to be different because we're looking at two different materials that have two differing properties. So delta T equals Q conduction of the concrete, delta X, negative Ka. So I just wrote those equations for both our brick and our concrete. So that means that the resistance of our concrete is going to equal delta X over the K of our concrete times the area. Resistance, sorry, I wrote that backwards. That's the second one that we're looking at. And then the resistance of our brick, which was that first one, is going to be resistance of our brick equals delta X over thermal conductivity, or K, of our brick times the area. So that's just those written out on the side there. And if we look at these in parallel, so the R total of our middle intersection here, so the brick and the concrete together, is going to be in parallel, so that'll be 1 over R B, and plus 1 over RC. So that's it in parallel, and that's the same equation that we had up here for parallel in general. I just put RB and RC to represent the resistances of our brick and concrete together. So now, if you remember from physics, you probably had to, after you add resistances in parallel with each other, you usually would redraw your situation to show those two resistances in parallel. So if we redraw this, I'm going to draw them as if they're in their resistances. So this would be what our example looks like now. We have the resistance of our heat, and then the resistances of the brick and the concrete now become 1, and they equal RT, which is just what I've denoted here. And then the resistance of our air is still there, and you'll notice that this looks just the same as our example in series. So then, to get your total resistance of the entire system, you would have to add these in series, so you do RA plus RT plus RH. And that would be your total resistance for the entire system. So the first thing you had to do was analyze the ones in parallel to put these into series, and then add them through series. So then you rewrite your equation, delta T. So the delta T would be the temperature of your heat the temperature of your air minus the temperature of your heat equals your heat flow, which remains constant throughout your system, and probably what you're trying to solve for, times your R total, which encompasses the brick and the concrete in parallel, as well as the heat, the brick and concrete, and the air in series. So that's, in general, how you would solve for an example that has both parallel and series resistors for heat flow. So now we want to look at another example with parallel and series, but it's going to be a bit more complicated this time. There's going to be a couple more components, but we're going to solve it the same way that we did the other ones, and you just make this easier on yourself by slowly going through each component one by one and not trying to do too much altogether at one point. So it's easier to add in parallel first, and then at the end add all of them in series. So the example I'm going to show you is going to be a little bit harder. Like I just said, it's easier to solve by doing parallel first and then series. But this example, with the way that it looks, it's actually going to be easier to do two of them in series first and then add them all together in parallel at the very end. So we'll go ahead and draw this figure. So at the top, I'm going to have two sections. One is going to be brick. Another's going to be an insulator. And then at the bottom, that covers both of those sections, we're going to have studs. And under that, we're going to have a two-paned window. So there's going to be two different glass pieces. I'm going to denote them as glass 1 and glass 2. So this is what our example is going to look like. We're showing a brick wall that has insulator on the inside, and that's going to be connected to a double glass pane. So that's like a glass window that is going to be made of two different glasses with two different thicknesses. We don't assume that these are all the same size, even though I drew them that way. So when you look at this example, you're probably thinking, oh my gosh, where do I even begin? And so, like I said before, you just break it down really simple and make it as easy for yourself as possible. So we're going to pretend like the left side is going to be the inside of our house and the right side is going to be the outside. So our heat flow will go from the inside of our house to the outside because the inside of our house is going to be warmer than outside. We'll just pretend it's winter, and that's going to be creeping through the wall. And we're going to look at the heat flow through conduction and convection at each of these areas. So I'm going to say the outside is air and the inside is just going to be heat. So we have RQ through convection of the heat on the inside of the house is HA dt. Q convection of the air, which is the outside of our house, is HA dt as well. Q conduction of our insulator is negative Ka dt over dx. Q conduction of our brick, negative Ka dt dx. Q conduction of our studs equal negative Ka dt dx. Q conduction glass 1, negative Ka dt dx, and the Q conduction of glass 2, negative Ka dt dx. So this is a ton of heat flows, and that might look super overwhelming, and you'd be like, oh my gosh, this question is going to take me forever to find what our heat flow is if I evaluate it at all of these spots. Or if you're trying to find the temperature between these spots and how that changes, that would take forever. So you're going to add your resistances in series first in series and parallel in order to get your total resistance, and that's going to make it easier for you to find the heat flow and how the temperature is going to change from inside to outside. So we can rewrite these again. So we'll write our insulator is going to have the resistance insulator, and that's going to equal our delta X over thermal conductivity of the insulator times our area. So that's like, once again, drawing back to how we found our resistances, depending on whether it's conduction or convection. We know that the insulator is going to be through conduction. So I'm just going to rewrite all of these resistances in this format. So the resistance of the brick, delta X, thermal conductivity of the brick times area. the resistance of our heat on the inside. That's going to be our 1 over H of the heat times the area. So that's the different one because the air of the heat inside the house is going to be through convection, not conduction. And then the resistance of the air on the outside, which is, once again, air, that's going to be 1 over H of the air times the area. Then the resistance of the stud is going to be delta X over thermal conductivity of the stud times the area. Resistance of glass 1, delta X over thermal conductivity of glass 1 times the area. Resistance of glass 2, delta X, thermal conductivity of glass 2 area. So these are all of our different resistances that we have here. The resistances that are through conduction are going to have those delta X, Ka terms, and the ones through convection are 1 over HA. And this is nothing new. This is the same thing that we've been doing. It's just with a lot more components this time. So now when you're looking at this example, I think it's going to be much easier to combine our insulator and brick together in series to make one big block at the top, and then combine our glasses 1 and 2 into one resistor at the bottom through series, and then do the top block, the studs, and the bottom block together in parallel to get our total resistance. I think that will be the easiest way for us to find that total resistance. So we'll start by adding the insulator and brick in series. We're going to denote this as being RIB because it encompasses the insulator and the brick. So you're going to add the resistance of your insulator plus the resistance of your brick together to get the RIB. Then at the bottom, you're going to add your two glasses together. So I'm going to make this resistance of uppercase G to represent both glasses. Add those in series because they're next to each other, not on top of each other. So to get from the inside of the house to the outside of the house, you're going to have to pass through both of the glasses to get there. You can't avoid one glass over the other. That's why they're in series. So that'll be resistance of glass 1 plus resistance of glass 2. So I've just written that down here to represent the two resistances, the two areas of resistances that we're going to add in series first. So now I'm going to redraw our diagram again since we changed two things. So we have the inside of our house here, outside of our house. Now on our top block, since we added the brick and the insulator in series, that's now RIB, so that's going to stretch the entire length of the inside to outside. Then we still have our studs in the middle, and on the bottom we have our resistance of the two glasses because we added those in series as well. So this is already simplifying our example much further. This looks a lot more easy to evaluate. And so you'll notice that in order to get from inside to outside, you have to pass through all three of these components. So these will be added in parallel to get our total resistance. So add all of our R's up. This is going to equal R total for the entire system. These are in parallel, so we'll do 1 over RIB, so that's our top resistance, which is the insulator and the brick, added together in series. The middle, which is our stud, nothing happened to that one, that's just the stud by itself, plus 1 over RG. which is the combined resistances in series of the two different classes. And that's how you're going to get the total resistance through this entire system after you've simplified it through series and parallel additions. So finally, our delta T, which is going to be the temperature of the outside minus the temperature of the inside, or final temperature minus initial, equals our heat flow, which is constant throughout our system, times the total resistance, which encompasses all of the components that you're going to have to pass through for your heat flow to go from one side to the other. And if we wanted to, we could take all of these resistances that we've written down here and substitute them into this equation, and that would have all of the components that we need to look at, all of the convection coefficients, the thermal conductivities. The cross-sectional area will remain the same for all of these components because we're looking at the same cross-sectional area, the different lengths. So if we substituted all of those in, that would look at all of those components in order to solve. But since we're just looking at the theory behind it today, we're just going to leave it at R for now. So that's going to be it for my video today. Hope you all enjoyed.